So what we have here is an emitter-follower circuit. This is a BJT transistor, NPN, and you'll often see this configuration used to buffer between stages. So it's used as impedance matching. It doesn't offer any voltage gain, as we'll discover, but what it does do is gives the ability to match sources. So here, this is the source. With the load, this being the load, this circuit becomes a buffer between the source and the load, so this source can drive the load more effectively. So if we want to analyze how this circuit works, then the best way of doing it is to consider the small signal model, the T model, otherwise known as the RE model. And if we redraw this using the T model, so that's our T model. So if we consider what the source sees, so we could label that as Z in, so the impedance looking into our overall circuit, and the load, what we're going to do is define that as Z out. So what that is the output impedance of the emitter follower that the load sees. So we're going to define Z in and Z out. So Z in, if we think about a few things before we start this, V in is, we could also say that that is the voltage at the base of the transistor, and the voltage at the base is the thing that is kind of across these two. So this is what we're calling VB here, across the little RE resistor, the internal say resistor. It's 26 millivolts divided by the IE value, the IEQ value, that's our little RE. But it's across the two impedances here. So we can say that Z in is equal to RB, and this is in parallel with the impedance looking in to the base, so ZB. So what is that impedance? Well, we can define that impedance simply by thinking about the currents and the voltages. So the emitter current flowing down here, think about it as 1 plus beta IB. So let's just start by writing out this ZB, and let's say that that is a relationship between the VB, the voltage at the base, and our current IB. So if we think about what VB is here, we can say that that is 1 plus beta IB multiplied by, we've got our RE, little RE, RE1, and we've got the parallel combination of RE and RL. What I'll do is I'll just say RP is RE in parallel with RL. So this is plus RP. So what we can see is whatever we attach to this emitter follower, it will have a bearing on the input impedance that this source sees, and that impact is really proportional to the differential between the base or the biasing resistors and the parallel combination of this input impedance looking into the transistor itself. So this is our overall expression, if you like, for the Z in. And in order to calculate Z in, we consider the load that's attached. Now, highly likely that as we add an RE resistor and an RL, that this is going to be somewhat bigger than the little RE impedance. So we can simplify our Z in equation somewhat. So just to recap, the RL, the attached load, does can impact the Z in, so we just got to look out for that. If we think about the voltage gain, AV, this is given as V out over V in. Well, V in, we've already specified that is this VB value. And what is the VB value? Well, we've got the VB value defined here. So V out is the combination of the RP, so the RL and the RE in parallel. So V out is equal to RP, and that's multiplied by the emitter current, which we know as 1 plus beta IB. If we were to put V out over V in, we can see that the 1 plus beta IB would cancel, so therefore the voltage output as RP divided by R1 plus RP. So we can see from that the combined parallel impedance of RL and RE is likely to be much larger than little re, RE1, so we can approximate that this voltage gain is going to be almost 1 if we negate this little RE1 here. So next, let's consider Z out. Z out, this is what the load resistor sees. It's the RE path in parallel with this path here and the impedances that are attached through the emitter. So we can say that is RE in parallel with, we'll call it Z in B. So Z in, let's call it E. So Z impedance looking into the emitter. So basically, what is Z in E? Well, it is the little RE1 in series with a combination of the source impedance, so let's call that RS, and the parallel combination of this RB. So we can say that it's RB in parallel with RS, so our source. Now, because in exactly the same way as we've got this IB and we've got this current multiplication here, beta IB, such that the emitter current is 1 plus beta IB. Looking back into the base, we do a divide by beta plus 1, and basically then what we can see is little RE1, maybe that's going to be a lot smaller than the RB in parallel with our source, but certainly what we'd aim to do in our design is make RB a lot bigger than RS, which means that the RB would be neglected in this equation, and perhaps also the RE1. So we're left with the R source divided by beta plus 1. In some texts, sometimes we see the Z out defined, the overall Z out defined as simply R source, so in our case RS divided by beta plus 1, but that is quite a simplification. The thing to consider is what we're doing there is simplifying just the Z in E. We've got to also take into account this value of RE, but let's just write out our Z out then. So that is RE in parallel with, well, let's assume that RS, our source feeding into RB, if we make RB large enough, then this is going to be RS over beta plus 1, negating the RE1 and the RB. So that is our Z out equation. So what this tells us is, in terms of the output impedance of the emitter follower that the load sees, it's related to both the RE resistor that it's attaching to in parallel, but also it is related to the source impedance that's feeding the follower. And likewise for the when we're considering the Z-in, we'll see that the Z-in that the source sees, so the overall impedance looking into the follower, the attached load has a bearing. So the output impedance, the output load is almost reflected back to this Z-in,